Hello, everybody. My name is Giscard. Thank you for your introduction. I work for Huawei, and today we're going to be talking how we hunt down network failures impacting customers in a cloud scale. I would like to ask advance apologize for my very bad accent, so please don't let that disturb you. Bear with me. Let's make it a good talk. Before we go what we do, let's try to explain how a packet flow in a cloud network. So imagine you have like a social app. Usually you're going to get some static content from a CDN, and you're going to do an API request to your service. Your service very likely we're going to access another database or maybe an object storage. Behind the scenes, how does that work? In truth, your packet will going to be sent to the internet, and we're going to cross some physical device that we call routers. And when you have to send your request to your VM, usually your VM has a private IP. So what you need is a public IP, which usually we call Elastic IP. The problem is an Elastic IP is not inside your VM. It's another service that we're going to handle that Elastic IP. And then it knows that it belongs to a customer. We're going to encrypt that packet and send that packet to your VM. No, because your VM is usually behind the load balancer. And it has to send this traffic to a load balancer. But the load balancer also is elastic and has several nodes. What does that mean is someone has to balance the traffic for the load balancer. So usually it goes to a network load balancer that we're going to do some magic, send to the application load balancer, which will send the packet to your VM. No, it still goes to a bare metal. And the bare metal, we're going to have to decap this packet to send to your VM. When your VM wants to access the object storage service, usually the service is shared. So it doesn't have like an IP that you can access it straight away. So we'll have what we call VPC endpoints. And this traffic go to the VPC IP service, which will then send the packet to the object storage at the end. I know it might sound a bit scared and complicated, but I promise you it's much worse than that. I oversimplify it a lot. What we're talking is this happening in a billion number of requests, and the number of nodes, it's in the scale of millions. So how do you find the problem? And when one of those nodes break, you're probably going to impact several customers. So before going to that, let's understand why you have all those complications with the packets. You know, what is this virtual private cloud thing? In a cloud, you usually have the bare metals. They are connected through a NIC. And to make your VM run, you install hypervisors, but hypervisors don't create VPC. So what you install also is what we call a virtual switch, so different customers can have their own VPC. Here you can see both customers took the same IP range. How do you deliver a packet with the same IP for different customers on the same machine? So what it happens is when the customer sends the packet, this packet is encapsulated in what we call a VPC header, and then it's encapsulated in the final IP header, and that is sent to the VM. And this is what we call outer header versus inner header, physical versus virtual, or underlay versus overlay. But that's not all. Usually you don't have full bare metals. You have like millions of bare metals. They're placed in racks, so you can provide service like VM or databases as a service, whatever. Those bare metals, they usually have to access disk. Even though they might have some disks, they have to access some ephemeral disks. And there's also racks with storage. So you can write your file or read them. Because you have those packets coming and going, it's not just physical network device. Usually you also have what we call virtual network device. So you have those racks full with those special hardware and software just to deal with packets like load balancers, firewall, NAT gateways, and those kind of things. And because cloud is not just about infrastructure, we also have racks providing some service, like an object service, an object storage service. And finally, you have some racks that it's a mix of all of them, because no one has a data center close to every customer house. So you have to put those racks close, what we call POPs, so the customer can access it in a low latency. Those things are placed in different zones because they have different secured restrictions. And one very special zone is what we call management zone, which is basically the software that manages the cloud, that configure the whole cloud for all the customers. And what I want to pinpoint here is network provides infrastructure for everyone. It doesn't matter if you're an external customer or an internal customer. If one of those physical devices break, it will going to impact traffic for a lot of people. It's very different from bare metal going down. A bare metal going down will impact the VMs on that bare metal. When a router goes down, it will impact a lot of people altogether. One more time, this is not all. There's much more than those types of racks. I'm just trying to oversimplify it here. When you put those racks together, you get what we call a data center network. And a data center network provides this network infrastructure for those packets between those racks. But that's not all. Eventually, your packet you're going to have to go outside the cloud. And then you have a different type of network that we call WAN, which is the wide area network that provides all the infrastructure for your packet comes into the cloud and gets off from the cloud. As everything in life, there's always people developing new technology, so you have different versions of those data center network because you have new bandwidths, hardware, which are more powerful. And of course, if you have newer versions, that means you have older versions. And if you have older versions, there are some Jurassic versions that you wish they wouldn't be there. And more recently, you also have this AI ML stuff, and then there is a new design for all the data center infrastructure because everything is totally different. So there's a lot of different designs and hardware that you have to support if you want to troubleshoot a customer traffic. When you put everything together, you have what we call a global infrastructure, which is a bunch of AZs and regions. And one thing I want to highlight here is those regions, they are connected between each other. And it doesn't matter if you pull the cable between those regions yourself, or you find a partner, or you rent from someone, it will break. And when it breaks, it impacts your customer. How do we deal with all this complexity nowadays to make sure we keep the network safe? Because it's very important. Well, let's start with the basics, which is those nodes have telemetry. And based on that telemetry, you can see if something is going wrong. Some of those devices, they are very rich in telemetry, like network, physical routers have been for decades. It's very rich. You have hundreds of telemetry. Hypervisors are usually open source or inspired in open source, so you also have a lot of telemetry. Virtual device is not that much, is not that good, because they are still evolving, and the teams are adding more telemetry to improve their reliability as it goes. The problem is everyone as an SRE knows you cannot just rely in node metrics, because sometimes the node doesn't provide the right metric. It can have bugs, or it might be under pressure. So we also do what we call end-to-end metrics, which basically we install agents in all those racks. We do a kind of a ping mesh, and then we can see that something is failing between the source and the destination. Of course, if you tell a network engineer, oh, there is a failure between Beijing and Dublin, the guy will say that doesn't help. So what you can do is, you know that from Beijing to Dublin is failing, from Beijing to Paris not, from Paris to Dublin is failing, so very likely Dublin is the problem. And then you can drill down to a data center network, to a rack up until you try to find the device. When you put all those information together, you can send to what we call a network monitoring brain that can take actions and decide which device or which area of the network is failing or not. So this tooling is very good to find multi-customer impact on the network, and also it's very good to keep it continuously running and monitoring everything. It has some limitations though. One of those limitations is, what if there is a single customer failing with like 10,000 of requests? This will be so small and the percentage of failure will be so tiny that you won't alarm. No one creates alarms for like 0.00001%. What happened is you're gonna have to tune those alarms to only keep metrics that are really finding some anomaly. And based on those metrics, you can try to figure out where the problem is. There's one more problem here, which is network was designed to fail. So not every packet being dropped means something is going wrong. TCP, retransmit, for example, so you just don't care if you lost one of the packets. Another problem is if Bob decides to do a soak test, oh, I'm gonna just smash my server and see what's going wrong, how much it can sustain. There will be packets being lost, but that's not the problem. You cannot act on that. It will be just too noisy. The another problem we have is those ping mesh thing that I mentioned, by having the agents send pings to each other, it doesn't mimic the final customer behavior because the customer goes through a load balancer and through all those VPC-IP. You can try to have those agents running on the VMs itself, but you cannot put an agent in every VM and stress every single node of load balancer, so it's limited. The other problem is when you see the loss between the source and the destination, you don't know where is the hop or the node that is failing. So there are some tools that can help with that. One of them is called SFlow, which you can sample flows in the network. It's sampling. Not every failure is 100%. To be honest, most of them, it's a few percent. So if you're sampling 10% of the packets, you might not see anything wrong if the failure is 1%. Another tool is called NetStream, which is per flow. They can collect some metrics. Then you can see more things. The problem is part of NetStream runs in what we call the control plane of a network device, which means you cannot use that much resource because the control plane of the device is supposed to do something else. So you have to be very careful. So all those tooling, I'm not saying it's bad, it's super good, it's essential. To be honest, it gets like 95% of the problem. It helps to fish. Where is the problem when you cannot see exactly where it is? At least you can narrow it down. But for troubleshooting, the final thing that you have to fix, they might not be great. And there it comes what we would like to have as an SRE engineer working in the network. What if I could get the customer setup of the VPC, map that to my virtual and physical, to my physical layer, and from the physical, from my virtual layer, and from the virtual map to my physical layer. If I could do that, it would be amazing for me to troubleshoot the problem. So this is the architecture of the system that tries to solve that. So basically, we have agents deployed on those bare metals on those physical devices supporting the virtual network. We have a web UI where the network engineer can ask for monitoring, to start monitoring a flow. This goes to a service that has information about all those bare metals and VMs and the network topology. It sends to the controller to distribute those tasks to the agents, so the agents can start to collect the traffic as the traffic flows into them. Those traffics flowing are mirrored and sent to a collector. And this collector, we're going to put those data together to do a final analysis. What's important about the collector and the analyzer is we just don't want to tell, hey, I think this is the device failing, because that still takes time. We want to analyze and say it's failing because of that. It would be much better for the networking case. I'm going to get in more details now how this traffic flows from the bare metal to all those physical nodes. So what's the idea? The idea is, what if I can put my network into a CT scanner and see what is happening inside? And the idea basically is, well, all those traffic coming out from the VMs, they go through those virtual switches. What if I can put mirroring action on those virtual switches and say, oh, for this packet that I want to monitor, please capture it and send it to my agent. Of course, because there's privacy, you just get the headers. Also, payload is not useful at all. And then you send that to the collector. Now the collector knows that the traffic left the host. When the traffic arrives at the host at the termination point, you can capture that packet again, send to the collector, and now you know when the packet left the source, it arrives at the destination. And you can have some metrics like how many packets was sent, how many was received, which is the packet drop. Or also you can have the latency, how much it's taking to go from one place to another. It would be so easier if it was just that. The problem is, in this path between source and destination, there is a world of things that can change the packet. So for example, if you have a load balancer, you are very likely to change the destination IP. So how do we handle that? And then it starts the nightmare. The first case that you have to cover is what we call vSwitch virtual device, which is very similar to the virtual switch that we have into the bare metal. So there's a packet coming and the packet come out. Those virtual switch, they are very flexible and configurable. So you can put a market in the packet comes in the packet comes out. You know that the flow changed, those headers changed. You can send that to the controller, and now the controller can adjust the configuration. So it's very simple to use. One idea, for example, use one of the registers that you can use in the buffer to mark the packet. The other case are some of those virtual devices, they use like NetFilter. And one thing you can do, also, one more time, very flexible tool. You can create your own configuration. You don't have to change the code. You can put some marks on those packets, know when it comes in, when it comes out. You can mirror those packets using an flog. And of course, here there is a problem because putting those marks is not always that easy. Not because it's complicated in terms of configuration, but because sometimes people are using those marks already. Remember, you don't own those devices. Some other team owns those devices, and they might be doing some magic with that. So you're going to have to find if they have some bits there for you and use them for your tracking purpose. Another type of application is what we call user space application using a normal socket. Example, NGX. So you have the packet coming through the kernel. The kernel delivers this packet to the user space application. The user space application will do whatever they have to do and send it back to the kernel. For the incoming part, it's kind of simple. You can use the BPF tracing. For the ones that doesn't know what's a BPF, it's like you can put a piece of code inside the kernel, whatever function you want, and get some kind of information and send that to your user space application. One thing here I want to highlight is, please, if you want to do that, you can use trace points or raw trace points, which is like kind of a standard interface, or you can use kprobe or func, which is more like ad hoc. But if the kernel changed those functions, you lost your tracing. So prefer the user API ones because they're much stable. One more problem with those kind of types of application is if the application changed the flow, how now your eBPF tracing knows how to monitor the egressing part? Because you don't have that information anymore. So here, there are some alternatives. One of them is you can provide a library to the users, to the owners of those applications, and ask them, please, use my library so I can map this flow, and then I can monitor that on the egress part. Some tooling like NGX, they already provide some features that you can know how the traffic was mapped, and then you can extreme those logs to your agent so you can get this mapping to know what's coming out on the egress interface. So eBPF, it's a great tool to help you on some of those cases. Those is what we call conventional applications. Nowadays, there's a bunch of new ones that we call XDP programs that are being created. And one type of XDP program is the one that runs in the kernel. It's very fast, so people like to use it a lot. But how do you monitor it? One more time, you can use eBPF. The problem is an eBPF XDP program, it's a eBPF program itself. So you have to create a tracing eBPF program that you're going to monitor the XDP eBPF program to get that information. If you don't know how to do that and might be in trouble, I would recommend to take a look at XDP dump. It's on GitHub. It's from Red Hat. They have like a very nice and short code there that does that. And it's very easy. I was very surprised. Another type of application is what we call AF-XDP applications, which is you still use XDP. For the ones that doesn't know what's XDP, it's a way to bypass the kernel. You tell the kernel, please don't deal with my packet. You'll take too long. Give it to me. I'm going to do that for you. And that's not because the kernel is bad. It's just because the kernel has to do a bunch of things, and maybe your packet processing doesn't. You know, you just want to drop a packet because there is too much. You don't need the kernel for that. You can do that yourself. Back to the AF-XDP program, what it happens is the packet comes to the kernel, and it's sent to your user space application. Then your user space application can do whatever they want with the packet and send it back. A good thing about AF-XDP is the user application, it knows everything about the packet. The packet is like a layer 2. They're going to have to change everything. So that application can tell you for sure how one flow is being mapped to another. The bad part is when the packet is coming off, it doesn't go through the BPF program in the kernel anymore. It goes straight to your TCQ. So you need another type of BPF program that attaches to the TCQ to mirror that packet and send it back to the agent. One thing I would like to note here is you can use kprobe here, kprobe. You don't need the TC, but one more time, kprobe is not formal and official user API, so you might run in trouble later. I'm almost done, I promise. There are some other types of application that we call XDP offload, which is it's the same eBPF XDP, but they offload that to the NIC. Imagine now it's inside the firmware or inside the hardware running inside the NIC. And here you're kind of lost. There's not much you can do. You will have to rely a lot on the version of the firmware, if the kernel support that thing or not. It's a nightmare. Thankfully, besides we had some experiment, we don't have that running in our cloud, so we were kind of safe, but this is a nightmare. You're going to have to align a bunch of firmware between several different types of devices. It's not an easy thing. There's also another type of application, this is endless, and the PDK, it's very common. And why people use the PDK is like, I don't like the kernel, I think the kernel takes too long, I would just jump the packet to my user space application and do what I have to do. The problem here is those DPDK applications, they're usually built for a very specific purpose. And what that means is they don't have all this flexibility that a virtual switch have. So here, unfortunately, there's not much you can do. You're going to have to talk to the team that owns the application and convince them to expose that packet for you. And to do that, we decided to use the vhost user, which is a UNIX sock behind the scenes. So it's super fast, and it works very well. One thing to highlight here, there's also the possibility to use uprobes, which is a eBPF that you put in the user application. The problem with that is every time you hit the uprobe, you have to interrupt and send the application to the kernel. And of course, if you build a DPDK application, it's because you don't want the kernel, you don't want to keep switching here and there. So you can use for experiment, but not for production. There's also something called ENPU, which is Ethernet Networking Processing Unit. It's a special type of hardware with special type of chips and how it does create those chips. That's very good to process networking traffic and also some custom applications. This one is even worse than the PDK in the sense, if you want it to mirror packet, there is no other way. You have to talk to people and get it there. It's a bit more annoying because it's more hardware specific related, so you might not win every battle. And finally, there's still a bunch of other things I will not mention here. There's always a lot of skeleton hidden here and there. There's also some unicorns, not the billion-dollar companies, but the things that should not exist, but they are there somehow. And you might not be able to fulfill or to support them. Well, but that's not all, because I was talking mostly about the virtual device. There's also the physical device, what you do with the physical device. And the idea here could be the same. Why don't I put an agent inside the physical device and ask that agent to enable SFlow or NetFlow for that specific flow I want to monitor? The problem is a network device, they scale are in dozens of thousands or hundreds of thousands. You don't want to configure every device every time you want to track a flow. So the idea was, why don't we put a mark in those packets? And then we know that this packet is someone that we want to monitor. One header of the IP protocol, both IPv4 and IPv6 support that, is the traffic class. And you can use that to say, this is a special packet, I want you to take a special action. One problem with that is those fields, they are usually limited. And for more that you think you are special, there are thousands of people fighting for those fields. And some of them, it's standardized, so better not to use them. Configuring a network device for that is quite, I would say, traditional. You can configure it to just match a specific packet and send that via GRE tunnel to your collector. And you can do all that in the ASIC. Remember, there is the control plane CPU and the ASIC of the network device, so it's super efficient. You won't impact the device at all done in hardware. The problem is physical hardwares can also sometimes change the packet. And then how do you know how the packets are being monitored from ingress to egress? So now what we are exploring is why we don't put this flag inside the VPC header, which is the VXLAN header. They have some reserved bits, and then we would keep the color of the packet through the whole process. There's another thing, which is when you start to mirror packets, it can get wild in number of packets. Just imagine like a 10 megabyte traffic change between two hosts. You can have like dozens of thousands of packets. So you cannot just handle all of that. So the idea is why we don't use in-band telemetry, which is between the header, IP header, and the payload, I can start to put some information to know where the packet is trafficking. In-band telemetry, it's not that new, but people don't use too much for a very simple reason. Not every device supports it. And people has to buy sometimes extra license to support it. Fortunately, Huawei supports in-band telemetry. We have that in our device, so we'll see how we can explore that. Another problem here is if you find a virtual device that supports in-band telemetry, that would be like making Jesus Christ. No, it doesn't happen. It's very rare. You're gonna have to do that yourself. So it's not just I will use it. You're gonna need people to implement that on their software as well. One thing, why do that? First, efficiency, and the other one, you're going to standardize. Because as you can see, this thing is becoming too complicated, right? You want to simplify it. Here is a screenshot that I would like to share. You can see here the diagram with the final user network configuration, how we map that to the virtual network, and how that's mapped to the physical network. I also want to highlight it's not just about showing where is the problem. For example, up here, you can see there's a failure in the network interface. But you also want to tell the network engineer why it's failing. In this case, what's a security group that was configured and just broke the things down. It was a customer failure. It wasn't Huawei fault, but it's an important customer. They pay support. You have to help them. So those things are very important, and they help to reduce the time to find where is the problem for the final customer. Of course, this is a very simple use case. There are much more complicated ones, but it's just to show how it works. We have it running today. There are millions of nodes onboarded, more than 300 users with 2K investigations every month, and it has speeding up the troubleshooting up to 8% of time. Why not 100%? You know, like it's quite clear where's the problem there. Why don't you automate that? There is still one catch here: is how do you find the flow? How do you find where you want to start and end your traceability of the packets? So what are the lessons learned? Like customer privacy is paramount. So you always truncate the header. You just use metadata. And here one thing: even IP headers. There is no need to show all IP headers. You know, if you're a network engineer, you don't need all the fields. You just need to understand this is the flow of the customer. You know, you don't need all the information. Safety: those agents will be deployed in hardware that you don't own. And those people owning those hardwares, they already have a lot of problem. They don't want you to causing more trouble to them. So have hard limits for all those agents, for everything they do. Have a one-click stop the word thing if things are going wrong, so you can stop what's going on. After all, we are a troubleshooting tool. It's less important than making the packet find their way. Support sampling. Some traffic can go really wild, so you have to support sampling as well. You might get everything, but you might want to get some part of it. Static config. All those dancings of, I'm going to enable that, disable that, and then I have to convert configuration between the device. More you touch something, more it can go wrong. So why not having a static config about the packet caller and just put the caller in the packet? So this can help reduce problems during the way a lot. The environment is very heterogeneous. So too many versions of hardware and software. Missing a device is okay. You know, you have nothing. If you can cover 10%, if that 10% of the device is like 50% of the traffic, you are in a good shape. Work with the other teams because their strategy might be very different from what you think. So you might have to converge so you can influence them and you make sure your system is going the right direction. And if you don't standardize, things will just get too complicated. For example, those use cases that I showed before, they're not all of them. There's much more. So you cannot just create an ad hoc solution for each one of them. What's next? We still have to close the gap for unsupported service. We want to work now on this standardization with the packet coloring. We want to have continuous monitoring because, as I mentioned, finding the flow is still very cumbersome. So how do I keep that continuous monitoring? Of course, you cannot monitoring every flow, it's too much, but how do you sample things here and there to figure out where is the problem? And if that's helping our engineers, that can also help our customers. I mean, why the customer has to call us to fix a security group? We might give that to them and let them then do the job themselves. Okay, that's what I have to share today. So I would like to thank you guys, and that's it.